Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to look at how to solve a system of three equations, three linear equations in three unknowns. And it's kind of analogous to what we did with two equations. We tried to take two different equations and combine them so that we had one equation with one unknown. If we start with three equations and three unknowns, we need to try to break that down to be two equations with two unknowns, which we can then solve the way we solved substitution or elimination. And with three unknowns, typically the best way to go is by trying to use elimination. And this is set up really well because all the coefficients in the third equation are either 1 or -1. And that means that we can cancel one variable from two equations. And the variable that I'm going to go after is y, because I've got a -y there, and my other coefficients of y are positive, so I don't have to worry about changing any signs. I'm going to label these first three equations, just in case, as equation 1, 2, and 3, just in case it'll make it easier to refer back to them later on. So I want to combine 1 and 3 to eliminate the variable y. And so let me just copy over those first. So 3x plus 4y minus 2z equals 14, and x minus y plus z equals -9. And I'm trying to combine these two equations so that y falls out. And so what I can do is if I copy the first equation over again, 3x plus 4y minus 2z equals 14, I can multiply the second equation, which is equation 3, by 4 to get 4x minus 4y plus 4z equals -36. And when I add these together, the y's fall out. I get 7x plus 2z equals -22. That's one equation with two unknowns. And I'm going to call this equation 4 for later. Next, I'm going to combine equation 2 and 3 to eliminate the variable y. Let me copy those down. The equation 2 was 3x plus 2y plus 3z equals -12. And equation 3 was x minus y plus z equals -9. I'm going to use the same approach here. This time I just have to multiply the second equation by 2. So that'll give me a 2y in the first equation and a -2y in the second. So copy over the first one as is, and multiply the second equation by 2. 2x minus 2y plus 2z equals -18. When we add, we get 5x. The y terms are eliminated, plus 5z equals -30. So that is a second equation that just has the variables x and z. So now we are moving backwards to solve a system of two linear equations and two unknowns. I'm going to start by rewriting equation 4 and 5. (7x plus 2z equals -22) and 5x plus 5z equals -30. We don't have one coefficient that divides into another for either variable. We don't have one coefficient that's positive and one that's negative for either variable. We can go after either of these. I'm going to get rid of z by multiplying the top equation by 5 to get 10z, and the bottom by -2 to get -10z. Notice the second equation, though, equation number 5, has a common factor of 5, and if I divide it through by 5, I might have something that I could solve with substitution. So if you're stronger with substitution, this one could work here. but I'm going to stick with elimination. I'm going to multiply the top equation by 5. 35x plus 10z equals negative 110. Then I can multiply the bottom equation by negative 2 to get negative 10x minus 10z equals positive 60. Negative 2 times negative 30. When I combine these, 25x, the z's are eliminated, equals negative 50. Now I've got one equation with one unknown, and I can solve that by dividing both sides of the equation by 25, and that's going to get me to x equals negative 2. So I need x, y, and z. I need an ordered triple to solve this system. I've got one of them. Now I'm going to back substitute, going back to one of the equations that had just x and z, and then I can find z because I already know x. So I'm going to go back to equation number 4. And so this is called back substitution, right? We get one solution and we work our way back to the others. So equation 4, again, was 7x plus 2z equals negative 22. I'm going to put in the negative 2 for x. Negative 14 plus 2z equals negative 22. 7 times negative 2 is negative 14, so I can add 14 to both sides of the equation. That gives me 2z equals negative 8. And if I divide through by 2, I get z equals negative 4. So now I have two pieces of my solution. I still need y. And I can come back at this point to any of these first three. I'm going to put in negative 2 for x. I'm going to put in negative 4 for z. And I'll solve for y. They all seem roughly the same, but I do like equation 2 because all the coefficients on the left side are positive, so I'll use that one. So I'm going to use this equation, 3x plus 2y plus 3z equals negative 12. Three x plus 2y plus 3z equals negative 12. I don't have it where I can view it, so I just want to make sure I copy that right. 3x plus 2y plus 3z equals negative 12. Got it? I'm going to take my two solutions of negative 2 and negative 4 for x and z, and I'm going to put them into this equation. So 3 times negative 2 plus 2y plus 3 times negative 4 equals negative 12. Negative 6 plus 2y minus 12 equals negative 12. Combine it in like terms, 2y minus 18 equals negative 12. Add 18 to both sides. Lost my negative sign. Careful there. 2y equals 6, and divide by 2 to get y equals 3. If I had not caught that I lost that negative sign, I still would have solved for y. But I don't know if I've got all the solutions correct because I really should check it in at least one more equation. So my solutions look like negative 2, 3, negative 4 as the ordered triple, but I should check it. And so I'm going to check it into, let's do equation 1. 3x plus 4y minus 2z. 3x plus 4y minus 2z, and I want to see if that equals 14. 3 times negative 2 plus 4 times 3 minus 2 times negative 4. That equals negative 6 plus 12 plus 8, and that equals 14. So it does check. You can check it in the other one as well if you want to be really careful, like on exam day where the points are really important. Checking it again is probably a really good idea. All right, so that's how we solve a system of 3 equations and 3 unknowns using elimination. In the next video, we'll take a look at a spin on that.